So good afternoon, everyone. My name is Ben Goldys. It is my great pleasure to announce a talk of Professor Tadahisa Funaki from Waseda University. And with this talk, for the first time, a topic of interactions between probability theory and partial differential equation appears in this seminar. This is, of course, well-known idea studied for many years, initiated perhaps by Kyoshi Ito from Japan. Professor Funaki has been working for many years on these interactions, and he's an author of fundamental works on particle systems and their convergence in some sense to mean curvature flows. So please, Tadahisa, you can start.
Okay. Thank you very much for kind introduction, Professor Ben Goldys. And I also thank all of the organizers for giving me this wonderful opportunity at this seminar. So my talk is based on the joint work with several people, mostly with Sundar Sesuraman in Arizona and other people. And the paper is already on the archive. I will talk on the two topics. First one is derivation of the motion by mean curvature from particle systems in this archive paper. And then I will talk about the coupled KPZ, derivation of the coupled KPZ from particle systems. That is my plan of today's talk. So I'm a probabilist, as Professor Goldys introduced. So I'm a bit afraid that most of the people in the audience are working on the PDs. But in a sense, my idea is related to the nonlinear PDs. What I want to talk about is the derivation of the nonlinear PDs or stochastic PDs, which has some stochastic term in the nonlinear PDs, starting from the interacting particle system. That is, we understand this is a microscopic system, and the macroscopic situation is described by nonlinear PDs or other things. As probably everybody knows, simplest case is the derivation of the linear heat equation starting from the independent random walks. So what I want to talk about is the generalization of this fact to nonlinear situations. To derive something nonlinear, we have to introduce some interaction among the random walks. And also we add the creation and annihilation of particles to these effects. So that is called the Grauber range process. So we consider on the d-dimensional, so square lattice, discrete lattice, but for simplicity, I introduce the periodic boundary conditions. And the size of this discrete lattice is n. N eventually goes to infinity because this is a microscopic system. Therefore, n eventually goes to infinity. So I just mark by circle the sites occupied by not only a single particle, but usually several particles. So several particles can sit each site, and each particle jumps to the neighboring sites. And I call the zero range part, that is a random walks interacting at the same sites. So interaction is very simple. If the particle come at the same position or the site I call, then there is some interaction. If the sites are different, then the particle doesn't interact from this part. And another part, creation and annihilation, is called the Grauber part. Grauber part actually governs creation and annihilation particles with some interactions among the neighboring sites, or the slightly wider range, but it's local interactions. I try to avoid the stochastic or the probability terminologies for the most of the audience working on the PD, but I should apologize in advance that my explanation may be not so sufficient to avoid enough. Okay, so that zero range part, that is the interacting random walks, produces nonlinear Laplacian, which you will see later. And Grauber part produces some reaction term. Therefore, macroscopically, we will see some nonlinear diffusion with the reaction term. That is actually Allen-Khan equation actually appears later. So I will talk about two results. In the first part, part A, I start from this global zero-range process on the d-dimensional periodic lattice. Then I will derive a motion by mean curvature and under some scaling in space. So macroscopically, the equation is on the continuous torus of size 1 because we shrink or the squeeze this microscopic torus by n. And the second part, I will talk about nonlinear fluctuation around, in a sense, around this one, but much simpler situations. Then we will derive a coupled KPZ equation, which I will explain later. There's some keyword, I just listed some keywords. The first keyword is the hydrodynamic limit, which means some local ensemble average comes out under the scaling by a local ergodicity. And the second keyword is the Boltzmann-Gibbs principle, which is in a sense much deeper so we take a first order term here, but the second order maybe first zeroth order here. Then the first and second order term is computed by Boltzmann-Gibbs principle. That plays an important role in our analysis. And from PD viewpoint, you will face a nonlinear Allen-Khan equation. Nonlinear means a Laplacian term is nonlinear. And the sharp interface limit, that is quite well understood or studied already in the PD group. And for the second part, you will see some ill-posed in a classical sense, some stochastic PDs. We need renormalizations in this situation, but I will explain later. So I come to the first part, that is part A, that is the derivation of the motion by mean curvature starting from interacting random walks with creation and annihilation of particles. That is a global zero-range process. And for the proof, that is a combination of the techniques of probabilistic method and PD method. In the probabilistic method, we use the relative entropy and Boltzmann-Gibbs principle, which I want to explain later. And the PD part, as I already explained, you will see nonlinear Allen-Khan equation and the sharp interface limit. But we have to prove this for the not the continuous Allen-Khan, but the discrete Allen-Khan equation. So we use, in a sense, from nonlinearity, some effective constant appears in the limit that comes from the correctors in the homogenization theory. That is expansion up to second order for this equation. And we use this equation, or even the discrete setting, we have a comparison theorem. We just combine these techniques, then we can derive the nonlinear motion by mean curvature from our particle system. This is the outline of my talk for the first part. So let us go slightly more in the detail to explain the microscopic particle systems. As I already told you, the particle moves on the d-dimensional discrete lattice under the periodic boundary condition of the size n. So it's n goes to infinity. Therefore, this is very large. And the zero range part means interacting random walk part. That is governed by the jump rate, gk. K is the particles on one single side. So depending on the particle numbers, jump rate of one particle is given by gk. So jump rate means if gk is large, then particle moves quicker. And if gk is smaller, then the particle goes slowly. So rate means something like a speed of the particles. So each particle moving, making random walks. And okay, so if gk is k, then each particle has the same jump rate 1. Therefore, this is the independent random walk. So this corresponds macroscopically to the linear Laplacian, usual Laplacian. But if GK is nonlinear, then we have some nonlinear effect. Then we have nonlinear Laplacian, as you will see later. And the situation at a single time, that is called the configuration of the particle system, is I denote by eta. So eta x, so each point is x. I call the position by x. And eta x means the number of the particles at the position x. And this jump rate depends on the number of the particles at the same site. So in this sense, interaction is governed only the particles at the same site. Therefore, we call this mechanism as a zero range. So I denote by eta this, including the particle number at each site x. Then ensemble makes a very important role. That is the equilibrium state for this interacting random walks. That is actually very simple, and product, because of the zero range property, it's product measures. And for each, if you fix the particle density, then for each particle density, we have some microscopic equilibrium state, which I call new rho. So macroscopic density, so if there are so many particles, or the almost, so if rho is 0, then there is no particle. So new rho is concentrated on eta, which has no particles if rho is 0. But if rho is large, then this is concentrated on the configuration with more particles. If you fix the average rho, then you have a new rho. And now we come to the Glauber part. Glauber part is the creation and annihilation of the particles. At single point, the configuration is eta, then the creation rate is denoted by, at the position x, denoted by Cx plus of eta. This is creation rate. As I said before, if C is large, then creation occurs rapidly, or Cx minus is large, then annihilation occurs rapidly. If this is small, then annihilation becomes rare. So rate is something like that. And we assume something, and then given these rates, interacting random walk part and creation annihilation part and initial configuration eta 0, then we can construct the time vibration of particles on this microscopic space T and D that I denote by eta t, or more precisely eta xt. And the x is the position, or the I call sites, microscopic sites, and the t is the time. And this is called the Glauber zero range process. Yeah, of course, certainly we assume some conditions on these rates, but I just skip it. Then I come to the scaling from microscopic to macroscopic. What we introduced is a microscopic system. So first, I fix the time, then you have a configuration eta like this. Then this is microscopic configuration. Then we move to the macroscopic configuration. That is, we squeeze the space by dividing by n. At the same time, the mass, original mass of each particle was 1. Therefore, eta x equal k means at the position x, mass was k, but we divide by n to the power d. So in a sense, microscopically, the mass is originally 1, but it's become very small. So we switch from microscopic to macroscopic by this transformation. So here, the delta measure originally at x, but we squeeze the space. Therefore, we divide by n. So this is a scaling corresponding to, we just squeeze the space by n. And because I use the x for the space variables for microscopic, then the macroscopically, the space variables denoted by v. This might be strange for you, but please accept it. And then we should introduce the time change for this eta t, which is a Glauber zero range process. And the time change for the so the time change is different for zero range part. The interacting random walk part is time change is n square. This is diffusive, usually diffusive. This is called the diffusive scaling. So space is squeezed by n. Then we speed up this random walk by n square. This is a usual diffusive scaling. And for the creation and annihilation part, we introduce another scaling, which I call k of n. But this goes very slowly compared to n square. But this eventually goes to infinity at the same time. Then under this time change, we have a process already introduced the time change, then eta and t. I denote it by eta and t. And my goal is combine, this is the spatial scaling or also the mass scaling. And this is the time scaling. We combine this operation and also this operation. Then we want to study what is the limit as n tends to infinity. Before discussing that, I come Allen-Kahn equation at intermediate level. So the goal is to derive the homogenized motion by mean curvature starting from our particle system. But before discussing this, I want to discuss first this Glauber part, K. That is, I first fix. So as I explained, K should depend on N. But first, we fix K. In a sense, we take two steps limit. First, we fix K. Then this is space and mass transform. The time change is only for the random walk part, diffusive scaling. Then actually we can derive some nonlinear reaction diffusion equation in the limit. This is a so-called hydrodynamic limit. This can be shown by showing the averaging effect due to the local ensemble average due to local ergodicity of the system, which I don't explain very precisely, but roughly saying this term coming from random walks. So in the if G is a jump rate for the zero range part, the random walk part, if G is linear, then this is actually just rho. Then you have a Laplacian rho. That is a usually people knows independent random walk case, but because of the some nonlinear effect of the interaction at the same positions, we have some nonlinear function here. This comes from the averaging effect, local ergodicity due to the local ensemble averages. And also the creation and annihilation gives local averages. So the creation rate is averages by the ensembles, which I already explained. So this is the ensemble or the equilibrium state corresponding to the random walk. And if a creation, of course, increases rho, therefore the sign is plus, and annihilation part, of course, decrease the density, therefore you have a minus sign here. So they're just ensemble averages. So first fix K, then we can derive a nonlinear PD like this, starting from particle system. But here, I just fix K. Then we have this nonlinear PDs in the limit by averaging effect for the rate. If G is large, then this becomes large, then the density moves much quicker. Then now we want to choose these two creation and annihilation rate in such a way that the following holds. So we choose the creation and annihilation rates such that the reaction term F becomes bistable this way. 3 zeros, F has 3 zeros, and F has this shape. So F is defined only for positive. Therefore, alpha 1, alpha star. Alpha star is actually unstable point, and alpha 1, alpha 2 are stable points. Maybe PD people knows very well. And I assume also the balance condition is satisfied. But because we have a nonlinear effect, and so I call this phi balance condition. Usually phi is a linear function in the linear Allen-Kahn equation case, then you don't have this one. But this condition means if you consider the potential W correspond to the F, but it is modified by phi, the bottom, so this is like a WL potential. And this balance condition corresponds to the bottom, two bottoms, has the same level. So we assume this condition. Therefore, we want to take creation, annihilation rates in such a way that these conditions are satisfied. Then this nonlinear PD, this one is called the Allen-Kahn equation because this is bistable and satisfy balance condition. But we have some nonlinearity in the Laplacian term like this. Then actually we can derive as k goes to infinity starting from this nonlinear Allen-Kahn equation, the homogenized mean motion by mean curvature. I think I'm not so sure about this PD result. This is just a purely PD result. Looks already new, but I'm not so sure as far as I know. But so first we fix k, then we can derive this, and then let k goes to infinity, then we can derive motion by mean curvature. But our goal is not like that. We want to derive the motion by mean curvature directly from particle system by making k depending on n, and at the same time, k goes to infinity. That is our goal. Yeah, I will come back. What is homogenized motion by mean curvature later. Now, but microscopically, the model has two different phases, sparse region and dense regions, roughly saying. Because of the choice of the C plus minus, we have two phase separations in a sense. So there is a phase separation, the dense area and sparse area. This is microscopic. And the interface separating two regions is not quite vague at the microscopic level. But if you move to the macroscopic level, then the interface, you can observe the interface more clearly. And then we want to derive the motion of this gamma t at the macroscopic level. So this is the main result of the part A. So as I already explained, we introduced the spatial scaling and mass scaling. And at the same time, we introduced a time change. And already we introduced also the time change for the Glauber part. That is the creation and annihilation part. Then our result is for roughly saying the following, this one. I'm not so precise, but we should assume some conditions on the rates and initial values, especially this holds at time 0 and the entropy condition. And we have to assume some additional conditions. And also k is very slow, but this goes to infinity, but very slowly goes to infinity. This is smaller than some constant times log n square root. So it's very slow. But by technical reason, we have to assume this condition. Then this macroscopic object after scaling converges to this already, the measure on the, maybe I should write dV, but this is a measure on the macroscopic torus TD. I consider under the periodic boundary condition. Then the limit is a step function, maybe times Lebesgue measures, because this is a measure. And this is a step function. And on the one side, this takes a value alpha 1. On the other hand, on the other side, this takes a value alpha 2, something like this situation in the limit. And gamma t moves in time. under this time scaling. And more precisely, it is improbability, but you should not care much. And the size is determined by, and gamma t moves according to the homogenized motion by mean curvature v equal lambda 0 times kappa. Here v is the normal velocity of gamma t, and kappa is usual mean curvature times d minus 1 at this interface. And the lambda 0 is a product of surface tension and mobility. In the next page, I explain. And I only consider the time up to the time t, gamma t stays smooth. So we don't have any result beyond the singularity for gamma t. This result is only up to the time gamma t is smooth. So this is the main result for the part A. And we have to assume some entropy condition for the initial values, initial data. And this is a very nice product measure. This called the local equilibrium. And this is a real system and entropy. We consider relative entropy. Relative entropy measures, in a sense, distance between two measures, mu and nu. And this means that this entropy condition means it is usually this is a volume order of n to the power d, but we assume this is already d minus some small positive constant. So this is small o of the volume. So in that sense, this and this is very nice measure, which is a product measure and the local equilibrium. So we assume these conditions. Then, we argument goes through the relative entropies, how this condition evolves in time. That is what we computed. And the lambda 0 is a product of surface tension and mobilities, and determined by these formulas. Actually, this denominator is mobility, and this 1 over this denominator is called the surface tension. So it's a product. So these has some physical meaning. Okay, so if for the linear case, lambda 0 is actually this is 1 and this 1, and therefore this is 1. This is the usual motion by mean curvature. But from the nonlinear effect, we have this one. Sorry, so 0 is a traveling wave solution for this Allen-Kahn equation, which maybe I will explain later. The proof of our main result is, as I told you already at the beginning, it's a combination of the probabilistic and PD methods. In the probabilistic part, we show the real system is close to, in a sense, close to the solution of the discrete Allen-Kahn equation by introducing a local equilibrium nu Tn. This is a product measure, but the mean changes in time and the space. This is a local equilibrium state, but it is determined by this discrete Allen-Kahn equation. Then we actually compare the real system with this local equilibrium by using relative entropy. That is the probabilistic part. So our result is that if the initial value satisfies, at the time 0, this real system is close to the local equilibrium in this sense. This is a small o of the volume, but slightly stronger than that. And if k satisfies this condition, then we can prove real system for the real system after time passes. It is close to this local equilibrium. Therefore, this is approximated by, in a sense, the solution of the discrete Allen-Kahn equation. So roughly saying that we use the entropy inequality and large deviation type estimate for this product measure, but this roughly says this macroscopic empirical measure is close to the solution of the discrete Allen-Kahn equation. And in the K actually moves. In the PD part, we will show that this the solution of the discrete Allen-Kahn equation converges to the motion by mean curvature, assuming some condition on the on the initial values. So for this is more technical, but maybe I don't have much time passes so quickly. So I use the Yau's relative entropy method, and also Boltzmann-Gibbs principle. In a sense, Taylor expansion in some sense, but okay, so maybe I just skip this part. Then in the PD part, I start from the solution of the discrete Arlen-Khan equation and derive the motion by mean curvature in this way. And combining probabilistic part and PD, this result, we can show the desired result. And to show this, with the comparison theorem for discrete PD, we have a nonlinear discrete PD, but we can, if we have a super and sub solutions, then we have a very nice bound because of actually the phi is a non-decreasing function. By using this, we have this comparison theorem. Then we construct super and sub solutions to show this result. And super and sub solutions are constructed. The leading term is a traveling wave solution corresponding to the original Arlen-Khan equation. And we need some cancellation to derive lambda 0. We also consider a next order term. That is sometimes called the correctors. Then this behaves in a very nice way, and we can show that we can construct the super and sub solutions by then making sandwich sub solution and super solution for the real solution, and the asymptotic behavior of the sub and super solution can be easily analyzed, and in this way we can derive the desired result in the theorem 3. And some related result. In the Kawasaki case, we consider zero range case, that is the random walks interacting at the same sites, but the Kawasaki is also random walks, but with hardcore exclusion interactions. So in the Kawasaki case, only one particle random walk can occupy each site, at most one particle. And for that model, we also did something similar with Tsunoda, and also we also considered the derivation of the Stefan problem, also two-component system with these people last year. Maybe I move to the second part now. So another problem which I want to discuss in this talk is the derivation of the coupled KPZ equation. So in this part, coupled means we consider multi-component system, but this is a stochastic PD, not a deterministic PDs. But it is known as a singular stochastic PD, that is ill-posed in the classical sense. But recently, this attracts much attention in the probability group because Martin Heiler and also Massimiliano and Gurinelli introduced a very nice some formalism to attack these problems recently. So in my case, I want to discuss a multi-component coupled KPZ equation that has this form. Coupled in the multi-component. So we consider the system. So if you ignore these terms, then the leading term is very simple heat equation and in the one-dimensional space. This is a very simple n-component system on the one-dimensional interval. Again, the periodic boundary condition, but we add the noise, xi I. This is a space-time Gaussian white noise. So this covariance, the delta measure structures. This means xi is independent if t or u are different. So we have an independent noise in time and space. And we have a nonlinear term. This is a coupling term. So Gamma is a constant, and then gamma is a coupling constant. And we have this kind of coupled heat equation with noise. That is, we call coupled KPZ equation. And we can slightly generalize the equation, but I just stay with this equation. And the gamma, the coupling constant, satisfies the bilinear conditions. That if you switch the role of J and K, gamma is the same. Actually, this is natural because if you switch J and K, this part is symmetric in J and K. Therefore, we can assume this bilinear conditions for gamma. But sometimes it is very convenient to assume the truly linear conditions. Bilinearity, I just symmetry by switching the role J and K, but trilinearity, I mean even I, that switching the role of I, interchange I by J. If you can interchange 3 IJK, it's the same. That is called the trilinear conditions. Okay, then the goal is to derive this equation from particle systems. But before saying that, the problem is the following. Even if gamma equals 0, coupling term is 0. So let's first assume the coupling term is 0. Then heat equation plus noise. Noise is very bad because of this covariance property. But Laplacian has a property to make the regularity of the noise better. But in the one-dimensional case, the regularity of the solution, even if the coupling constant 0, it is 1/4 slightly bad in time and 1/2 Helder in space. Therefore, the regularity in space is 1/2 Helder, at most slightly bad, like a Brownian motion. Therefore, if you take a derivative, then it is already the distribution, not the usual function. Therefore, this is a product of the two distributions. Therefore, you cannot give any natural meaning to this. Actually, so in this sense, KPZ equation, even without coupling, is ill-posed. Then, as I said, Martin Heiller introduced some nice theory to solve by introducing denormalization techniques. And I want to explain the role of the trilinear condition T. And for instance, just drop the noise term and just take a nonlinear term. Then we compute some energy estimate or to derive the energy estimate or a priori estimate. We just compute this, the derivative in space and L2 norm squared. Then we have something like this from the nonlinear term. Then if gamma satisfies the trilinear condition, then this vanishes. This is in a sense very similar to Euler equation or the Navier-Stokes equation, I would say. So trilinear condition has a very nice property that this vanishes, at least to compute some a priori estimate for the solution. But of course, this doesn't work because we have a noise. But okay, so before deriving the coupled KPZ equation, we have some result with Hoshino, which appeared some years ago. And the local solvability of the coupled KPZ equation can be shown without assuming the trilinear conditions, but the local solvability in time due to Maximilian's techniques, which is called the para-controlled calculus. Under the trilinear condition, we have global solutions by the, actually, as I explained, you can imagine it has a nice energy inequalities, the a priori estimate, and then we can identify the invariant measures, and so on. And motivation comes from some physics, the mathematical physics. So our goal is derivation of the coupled KPZ equation again from microscopic systems. So now, to derive the coupled system, we need the n component system. So we consider, so in the first part A, we discuss a single component case. But now to derive the n component system, we consider maybe n species system. So there are n different types of particles. They are making random walks. And now we only consider 1D because even for the KPZ, higher dimensional KPZ is ill-posed in even the multi-hierarchy sense. Therefore, we have to restrict ourselves to 1D case. Then in the first part, only we consider eta x, but we introduce n different species particles, therefore eta xi. Then we again consider the zero range process, interacting random walks. But this interaction happens at the same site, but with even with another type of the particles also. Then there is some works by these people that the invariant measure or the equilibrium states are totally characterized under some conditions. And it becomes product measures. But in the part A, this was rho. Rho was a single component, but here the average has n component. And now we introduce some weak asymmetry for the jump. So in the first part, jump was symmetric to each directions. But here we introduce some weak asymmetry. It is essentially 1/2 to the right, to the left, but slightly it goes particle jumps slightly more to the right compared to the left. Then maybe I don't have much time. Then I go to KPZ fluctuations. Now, okay, so we consider only, as I said, we consider the jump rate to the right and left, and we only consider under the equilibrium state. In the first part, we consider non-equilibrium system, but here we consider equilibrium state. Already initial distribution is equilibrium state with some density given by A0. A0 is a vector. And then we again introduce a scaling in space, x corresponding to x divided x. This is the same. We squeeze the space by n. That is the same as before. Then also we subtract the mean. So we consider the fluctuation of the process around this mean. So now we consider the fluctuation around the mean, but only under the equilibrium situation. Then, like a central limit theorem, actually, we divide by, in the first part, we divided by 1, we divided by n to the power d, so it's divided by n in the 1D case, but now we introduce the square root n. This is similar to central limit theorem scaling. And important is we have to introduce a moving frame to cancel, in a sense, the first order term. We introduce this frame moves very rapidly. Then scaling scaled. So this is a macroscopically scaled object. The space variable is, sorry, denoted by u. Originally, microscopically, the space variable is denoted by x, but macroscopically, now it is denoted by u. Then, this is the main result for the part B. We can derive something like a KPZ equation, but actually KPZ equation, so this is called the KPZ Vargas equation, because compared with the KPZ equation, we take a space derivatives. Then we take some constants appears, but just ignore these constants. Then if you take a space derivative of the KPZ equation, then we have this equation. Therefore, it is called the KPZ Vargas equations. And these constants, of course, comes from the microscopic systems jump rate of the zero range interaction rate. And also, we can slightly make more general, add some drift term, but essentially, starting from microscopic system, we can derive this KPZ equation in the limit. The proof, again, we use the second order, so Boltzmann-Gibbs principle. And by the this frame properties, we have the first order, zeroth order and first order cancels, and only the quadratic. So in some sense, this is the Taylor expansion and quadratic fluctuation term survives. Then we have these quadratic terms. Usually linear fluctuation problem is well studied, but this is a nonlinear fluctuation. That comes from the, by the scaling, we pick up the scaling in the proper way, then we pick up this second order term in the limit. We use some energy solution technique. This is for probabilist martingale problem solutions. This is a kind of martingale problem. So martingale problem is more easy to fit to derive some limit theorems. And okay, compared to the single component system, it was used, say that the beaming Kohlhoff transformed works for the single component system, but for this system, such kind of technique doesn't work. Maybe I don't have time, so this is a summary of my talk. Part A, I discuss derivation of the motion by mean curvature with homogenized effect from the nonlinear term. And also in the second part, I discussed the nonlinear fluctuations. Okay, so I thank the audience for your attention to the talk. Thank you very much.
Thank you very much, Tadahisa, for very interesting talk. And now it's time for questions. Who would like to ask? Now everyone is unmuted, so we can ask questions. So any questions?
1 second. Kazuka can speak.
Yes?
Yeah.
Thank you. I'm Keisuke Takasawa from Kyoto University. So how about the uniqueness of the limit of the first part of your talk? I mean that the uniqueness of the mean curvature flow.
So we assume that there is a smooth solution. So anyway, it should be, it's so unique that I don't know, but anyway, the limit satisfied this, so maybe this, and this is this evolves the motion by mean curvature. So I'm not so sure. I don't study anything about the motion by mean curvature itself. So we proved this converges to this one, and this evolves this motion by mean curvature. That's all. So, but we assume the gamut is smooth. Is that okay?
Okay, thank you very much.
Okay, thank you.
Hi, Changfeng Gui from UTSA.
Mm-hmm.
For this PDE unkind equation, you have this phi for the nonlinear part. What's the meaning of this function in your setting?
This one, this
The
phi comes from the interaction of the random walks. So this is the average of the rate of the interactions. If G is a linear function, then the phi is linear. So then you have a usual Allen-Khan equation. But because of the interaction, you have some nonlinear effect. This is the average under the equilibrium state, or the ensemble we call it, or maybe in the statistical physics, it is called ensembles. So we have a long time average by ergodicity. You can replace it by ensemble average. That gives this nonlinearity.
I see. Thank you. Yeah.
Any more questions?
Yes, I do have a question.
Yeah,
Hi, this is Boris Bäumer from the University of Otago. You said that your solution or your interface field of gamma of t in the first part, it might develop a singularity or it might become non-smooth. How could that happen if you're driven by the curvature?
So I expect it should be the solution of the, say, viscosity solution method. Maybe it should work, but we only consider up to t. So that is maybe the next problem. But I only stay at the classical regime, not beyond that one. That is very interesting question, I think.
Mm-hmm.
Actually, a long time ago, Suganidas studied with Katsurakis, I think, a different model, but a linear Laplacian case. He claimed he can derive beyond the singularity by using the technique of the viscosity solutions, but it's a long time ago. But in our case, it's nonlinear. We have a nonlinearity also. So I think probably it should be doable in this setting, but we don't study yet. And it should be a very interesting question, I would say. Is that okay? Mm-hmm.
Thanks.
Any other questions? No, I would have one question.
Yes.
Also about the first part of the talk. You mentioned Suganidis. Suganidis also suggested to use mean curvature stochastic equation for mean curvature flow with thinner noise in order to identify in the limit of small noise to identify one of the solutions when there is no uniqueness. Is it possible to modify the particle system in such a way that you will get stochastic equation of mean curvature flow?
That is an interesting question, which is, so it's, he worked with IP, I think, a long time ago. Also, yes. Which I know, but I don't know what happens in this setting. That should be, as I said, it should be very interesting, but actually, I don't know. It should be, so he picked up from the several candidates, the one natural one by using. So it should be very interesting, but I don't know. I have no answer, sorry.
Any more questions? So I would have one more question about the second part of the talk.
Yes.
You have this coupled system of KPZ equations and you have invariant measure for this system.
Yes.
Yes. What is known about the properties of the transition semigroup in the with respect to the invariant measure? Do you have ergodicity, reversibility, anything?
So we have. So this is what I know for this system. This is pathwise solutions. And we have under trilinear condition, we have to assume this one. But for the local solvability, we don't need this one. But for the global solvability, we need the trilinear conditions. Then we have a global existence like the Plato Vichy did for the Navier-Stokes case. And we use a strong Ferrar property for this system. Strong Ferrar also holds. And so for each initial values, we have a global existence. So we can connect this result to this one by using the techniques. I think the Plato and the Plato and the Vichy did long time ago by using a strong Ferrar property, which is shown by Martin Heiler and also I think Mattingly. I think something like that. Yes.
Thank you. Any more questions?
Yeah. Hugh Cooney has a question.
Thanks. Can you hear me okay? Yeah, so Hugh Cooney from Tokyo Tech. I'm just also wondering about in the convergence of the Alencon mean curvature flow. So typically you obtain some sort of equipartition of energy result. I'm wondering if in the stochastic setting you get some sort of, I don't know, approximate equipartition of energy in the limiting measure?
Sorry, I don't know. So you have some technique to show the convergence of this sharp interface limit?
Yeah, so in the sharp interface,
by using some energy method?
Yeah, so you look at the energy measure, the discrepancy measure, and it should vanish in the limit. I'm wondering if in the stochastic setting, something similar happens.
So I don't know, but I once discussed with Tonegawa in the Tokyo Institute.
Yeah, he's my
so
supervisor.
Okay, so I asked this discrete system, so his method does work or not, but eventually his answer was negative. So I don't know.
Okay, thanks.
Yeah, you should ask Tonegawa.
Okay.
Okay.
Any other questions?
Yes, Koji Okitani has also a question. He could maybe raise their hand.
No, please.
Yeah, he can speak now. Koji, can you? Sorry. Can you unmute? Okay, you can speak now. Koji, you can speak now.
He probably can't hear us, or
I don't know, maybe his microphone is not working. So I can also read his question. So he's asking, is it possible to have a lattice model which leads, for example, to a square root Laplacian?
Square root Laplacian, I think it is possible. Also, so it's long range jumps. So we consider only the jumps to the neighboring sites. But square root Laplacian or the even much more general type of fractional powers, that should be possible also. But instead, we have to consider random walks with long range jumps. Some people studies, but in a different setting. In this hydrodynamic limit is studied by deriving long range jumps. Is that fine?
Yes, I think so. Kokchi has microphone problems, so
okay.
Yeah, he says yes, it's okay.
Okay.
Are there any other questions? So if not, I think we can thank again Tadahisa for a beautiful talk, and to thank all participants and all colleagues who asked questions. And now everyone is invited to the coffee break in a few minutes. Everyone should have received an email with the link to the next Zoom meeting for the coffee break, when we can ask more questions and we can discuss and chat more freely. Okay. Thank you, and we can close this meeting now. Thank you very much.